Hello, and welcome to the Software Carpentry lecture on object-oriented programming. In the next few episodes, we'll explain what classes and objects are, and show you how they can make big programming projects easier to manage. Computer science is many things, but at its heart, it is the study of algorithms. Computer programming is also many things, but when everything else is cleared away, it is about creating and composing abstractions. An abstraction is something that hides details or makes one thing act like another so that we can use them interchangeably. We have already met functions, which turn many steps into one larger logical step, and libraries, which group functions together to make them more manageable. In this lecture, we'll look at classes and objects, which combine functions with data to make both easier to manage. As we'll see, if they're used properly, they can do much more than that. To understand the problems object-oriented programming is meant to solve, think about writing a program to simulate an aquarium containing plants, snails, and fish. Plants don't move around and nourish themselves through photosynthesis. Snails crawl around on the floor or walls of the tank and scavenge food, while fish swim in 3 dimensions and hunt for food, including each other. Conceptually, the algorithm for simulating all of this is simple. For each time step in the simulation, everything in the world moves, if it moves, and eats, if it eats. Once that's done, we redisplay everything that hasn't been eaten. The program that implements this is more complicated. Let's start with the function that moves things. For each thing we have, we check to see if it's a plant, a snail, or a fish. If it's a plant, we don't do anything. If it's a snail or a fish, we call a function that knows how to move something of that type. So far, this is pretty simple. But what about eating? Again, we loop over all of the things in the aquarium. If the thing is a plant, we call our photosynthesize function. If it's a snail, we give it to scavenge, and if it's a fish, we call hunt to see if it catches anything, and if it does, we call devour to handle the details. This will work, but an experienced programmer would be feeling uneasy by now. To understand why, let's look at our third main function, show. Sure enough, it has a loop that uses the types of the things in the aquarium to decide what specialized functions to give those things to. This is starting to look familiar. As we said before, code that's repeated in 2 or more places will eventually be wrong in at least one. In this particular case, imagine what happens if we want to add starfish to our aquarium. We have to modify 3 functions in 3 different places. Remembering those 3 places is a burden on us, and even more of a burden on someone who's new to the code but wants to extend it. And what about fish that eat plants, or scavenge like snails instead of hunting one another? If we have to add ifs and elifs to our functions for each of these cases, our program will quickly become a tangled mess. Now, if you're an optimist, you'll look at this and say, every pattern in a program is an opportunity to shorten that program. Object-oriented programming was invented to handle exactly this situation. It lets us connect data and functions together so that we can write code like this, where each thing in our simulation knows how to move itself, how to eat, that it's supposed to tell us what it ate if it ate something, and so on. Contrary to some people's claims, there's no evidence that this is somehow more natural than any other kind of programming. However, it is easier to understand programs that are written this way, particularly large ones. And it's much easier for those programs to grow piece by piece over time. The next few episodes will show you how to work with classes and objects in Python, but before we do that, a word of caution. Nothing is free. Object-oriented programming actually does make very simple programs slightly more complex, and if classes and objects are used too enthusiastically, they can create just as big a mental burden as no abstraction at all. It's easy to see why too little abstraction makes things hard. People reading the code have to put the little steps together in their head to construct the big picture of what the code is doing. If there's too much abstraction, though, it will be just as hard for readers to translate those abstractions back into concrete actions in their mind to figure out what the program actually does. This becomes easier with practice, but beware of trying to do too much too quickly. With that warning out of the way, let's have a look at some simple classes.